Before radar existed, Britain built giant ears along its coastline. An operator would stand before a massive curved concrete dish, press stethoscopes to his ears, connected by rubber tubing to a trumpet-shaped collector, and listen. He was listening for enemy planes crossing the English Channel, picking up engine noise miles before any human ear alone could catch it. The dishes were shaped into precise parabolic curves, some stretching 200 feet across, engineered to do one specific thing: concentrate distant sound and deliver it, focused, into a human ear. This video walks through exactly how that system worked, and why the engineering behind it was far more deliberate than it looks. The ears themselves don't look like ears. If you walk past the concrete mirrors at Denge today, the most natural assumption is that you're looking at some kind of industrial leftover. A water tank, maybe. A retaining wall. The shape doesn't give much away, and there's nothing attached to it anymore that would tell you what it was for. But that shape was everything. It was the reason the system worked at all. What it actually was a dish. A large curved concrete dish, anywhere from 20 to 30 feet across for the smaller bowl-type mirrors, set either into the ground or mounted against an earthen bank, with its open face aimed directly across the English Channel. The curve wasn't decorative. It was parabolic, meaning it was calculated to do a specific job: take sound waves arriving from a distant source and redirect them all toward a single point in front of the dish. The operator's job was straightforward in description, demanding in practice. He moved that collector slowly across the focal zone, listening for the low, rhythmic throb of aircraft engines. When the sound reached its peak, when the collector was sitting exactly where the parabola directed the concentrated sound, he stopped. The position of the arm told him the bearing of whatever he'd just heard, read directly off a calibrated scale built into the mounting. Later installations replaced the trumpet and tubing with a microphone and electrical amplification, but the mechanical principle was unchanged. For this to work, the concrete surface had to be accurate. A parabolic curve that's off by even a few inches doesn't concentrate sound. It scatters it. So construction wasn't a matter of pouring concrete into a rough mold and leaving it. It required careful formwork, set to precise geometric specifications, and in some cases, the reflective surface was hand-finished afterward to bring it within tolerance. This was skilled construction work, not general building. The bowl-shaped dish mirrors were one design. But engineers also developed a second type: long, curved walls stretching 200 feet or more, oriented horizontally rather than as a full dish. These wall mirrors didn't give the same directional precision as a bowl. They couldn't pinpoint a bearing as tightly. What they gave instead was raw amplification across a much wider arc of sky, trading accuracy for range and sensitivity. If something was out there, the wall mirror was more likely to hear it. The bowl mirror was better at telling you exactly where it was. What you're looking at then, when you stand in front of one of these mirrors, is a precisely engineered acoustic instrument. Not a ruin, not a wall, not a tank. Concrete and geometry working together to pull the sound of an aircraft engine out of the background noise of wind and open water, and deliver it, concentrated, into a human ear. The engineering behind that was deliberate, the construction demanding, and the physical scale of these structures reflects exactly how seriously the problem was taken. The basic problem was time. The English Channel between Dover and Calais is roughly 21 miles wide at its narrowest point. An aircraft flying at 100 miles per hour covers that in about 12 minutes. So the mirrors needed to be as close to the water as practically possible. Every extra mile of detection range over open water translated directly into extra seconds of warning time, and those seconds mattered. But sitting right on the shoreline created its own problems. Wind off the channel was constant, and it carried noise, waves, shipping traffic, the low rumble of coastal industry. All of that competed with aircraft engine sound in roughly the same frequency range. Put a mirror too close to the water's edge and the operator spent most of his time filtering out the sea, which wasn't something a human ear could do reliably for hours at a stretch. The sites at Denge near Dungeness and the earlier installations near Hythe were positioned on flat, open ground set slightly back from the immediate waterline. Natural earthen banks and low ridges sat between the mirrors and the worst of the wind, knocking down ground-level interference without blocking the acoustic path across the channel itself. It was a careful balance. Enough shelter to hear, not so much that the mirrors were effectively pointing at a wall of earth. Dungeness had an additional advantage. The headland projects further into the channel than the coastline on either side of it, which pushed the mirrors at Denge a few extra miles closer to the likely approach corridors from northern France and Belgium. On a map, it looks like a minor geographic detail. In terms of detection range, it was directly useful. And if you want more videos on the machines that shaped history before modern technology replaced them, subscribe. There's a lot more of this coming. One constraint shaped every sighting decision in a way that had no clean solution. The mirrors couldn't move. Once a bowl or wall was poured and set, its orientation was fixed permanently, aimed at a specific compass bearing, covering a specific corridor of sky. Engineers had to decide, years before any aircraft would actually approach, exactly which direction the threat would come from. Get that wrong, and the mirror was watching the wrong piece of sky. The partial answer to this was to build multiple mirrors at the same site, each aimed at a slightly different angle. An operator at one mirror might hear nothing while the operator at the mirror beside him, facing a few degrees further north, picked up a contact. Together, those two bearings allowed a rough triangulation, not precise, but enough to establish a general direction of approach and pass it up the reporting chain. That reporting chain ran inland by telephone. A contact detected at Denge was called into a central coordination point, where it could be checked against reports from observer posts along the coast and cross-referenced with any visual sightings. The mirror wasn't the whole system. It was the seaward end of a network that extended well into the interior, with each node covering what the others couldn't. The individual mirror was a fixed instrument covering a fixed arc of sky, but the network those mirrors anchored was designed around the principle that overlapping coverage from multiple stations could compensate for what no single post could do alone. A bearing and a rough altitude estimate. That's what the mirror actually produced. The operator telephoned those two pieces of information to a reporting center, where plotters marked the contact on a map table and began tracking it. From that point, the clock was running. At 100 miles per hour, a contact detected 15 miles out over the channel gave the defense roughly 9 minutes. 9 minutes to alert searchlight crews, position gun batteries, and if fighters were available, get them airborne and pointed in the right direction. That was tight but workable. By the mid-1930s, though, frontline aircraft were regularly hitting 150 miles per hour, and that same 15-mile detection range now gave less than 6 minutes. The arithmetic was getting uncomfortable. Searchlights were the first thing that moved once a bearing came in. Crews along the coast swept their designated sector of sky, trying to pick up the aircraft visually. And a visual fix was worth far more than an acoustic bearing, because acoustic bearings carried real uncertainty. The operator was doing his best, but sound bends in wind, reflects off terrain, and fades unpredictably with distance. A searchlight that actually found the aircraft gave the gun crews something solid to work with. The anti-aircraft batteries were positioned to cover the same corridors the mirrors were watching. This wasn't coincidental. The gun network and the mirror network were planned together, each one filling gaps the other left open. The mirrors provided the earliest warning. The searchlights converted that warning into a visual track. The guns were the terminal response. Each stage depended on the one before it functioning well enough to pass something usable forward. What finished the acoustic mirrors wasn't radar appearing overnight and replacing them. It was aircraft getting faster year by year through the mid-1930s. By 1935, frontline aircraft were pushing 200 miles per hour. At that speed, 15 miles of detection range gave less than 5 minutes of warning. Barely enough to alert a gun crew, and nowhere near enough to get a fighter into position. And faster aircraft also flew higher, where engine sound attenuated further before reaching the mirror. The ambient noise of a busy coastline, wind, shipping, The general low-frequency clutter of the channel stayed constant while the signal the mirrors were trying to hear got weaker and arrived later. The mirrors at Denge never intercepted more than a handful of aircraft. By the time the network reached its most developed form, the planes it was built to detect had already outpaced it. But the reporting chains, the observer networks, the coordination procedures, all of that transferred directly into the radar era. The organizational framework was already built. Radar slotted into it. Radar changed everything, not because it was louder, but because it didn't need to listen at all. It sent out a pulse, waited for the reflection, and could track an aircraft at 100 miles in any weather, any wind, any background noise. The problem the giant ears were built to solve? How do you hear something coming before it arrives? Radar answered with a completely different question. What if you didn't need to hear it? The concrete is still there.